Greetings. This is going to be a short lecture discussing about domain of a rational function. Now I have already uploaded a 5 minutes lecture about some information related to this lecture, and I do encourage you to possibly watch that video first. Okay, then let me stay out of way, zoom the material that I have on the board, and start our lecture. May I do that, please? Okay, first let's find out what a rational function is all about. Rational function is a function of a rational algebraic expression. And rational algebraic expressions are those expressions in the form of P of x over Q of x, where P of x and Q of x are polynomials. And the polynomials that we are discussing in this lecture are polynomials of one variable, non-constant, single variable polynomials. And the denominator, the x values for the polynomial cannot assume those values that make the denominator 0. Okay, now let's go to the main body of the lecture. Now this is the function I selected to discuss about when we are interested to find about the domain of this function. It's a rational function. The numerator is a polynomial, denominator is a polynomial. Now as I mentioned in the previous lecture, there is a good relation between rational function and rational numbers. So let me also mention that one. So the 28 over 60 is a rational number. So according to the fundamental theorem of arithmetic, I went and decomposed that one into product of corresponding prime numbers of the numerator, and I did something for the denominator, and then I started to cancel out those factors that numerator and denominator they have in common. You notice I factored them out, I canceled them out. So I end up with 28 over 60 to be equal to 7 over 15. Now these two are equivalent. Equivalent means they are equal, but they look different, all right, in that case. Now, corresponding to this analogy, I also do exactly same thing for this function. So what I did, I went according to the fundamental theorem of algebra, I broke that one down into the factor form, corresponding factor form. In this case, end up to be 1, 2, 3, 4 linear factors and one irreducible quadratic factor. And then I did the same thing for denominator. Then I started to cancel those factors that they have in common, numerator and denominator. And I end up with this simplified form of it. Now, according to what I said a few minutes back, the denominators, x cannot assume the values that denominator becomes 0. So in this case, x cannot be what? Cannot be 7. So I wrote this one in set raster notation, and then also in interval notation, as you notice. And I also went ahead and sketched the graph of it for just presenting them in pictorially in a sense. Okay then, now let me zoom this one and say a few words if I may. Lo and behold, now comes the moment of truth. The moment of truth is that the solution that I gave you is wrong, is incorrect. Surprise, huh? Now, I went through all this labor, putting them in nice looking, using nice different colors and nice and clean, and they were all wasted in a sense. So now let's see what went wrong and what will be the correct answer. So let me now go ahead and zoom the correct one, if I may. Now, f of x is equal to this, and this corresponds to this is okay, that's correct. But f of x and equal to this equality is false. So that means f of x equal to this is correct, f of x equal to this as long as they are not cancelled. But here I cannot say, let me see if I have a red pen, yes I do. I cannot say that these two are equal. Do you follow me? So I have to put a big red color and say they are not equal. And then I also have here, now this and this are two different functions. So I cannot say f of x equal to that. Now let's call this one g of x. Now g of x is the domain of that is all numbers except x cannot be 7. Do you follow? Because if x is 7, we get division by 0. But where this original function given to me is defined for all values of real numbers except 0 and -1 and 1 and 7. You see the difference? So there are two different functions, and the graph of them are two different graphs. So that is very, very important to consider. But when you take the calculus, it's different. Then they will be taken limit, and then cancellation means different thing in when you take calculus. But anyhow, that is subject way ahead of you when you will be taken later on, hopefully. Okay, then also I also wrote this one. Let me take this one out. I put it no, so that do not bring about any kind of confusion. So that solution that I give here is a wrong solution. And I also end up with an angry face, which means this answer is not correct. Okay, now let's go and see what will be the correct answer. So the correct answer is that the domain of any polynomial is all real numbers unless it is restricted. So the domain of numerator is all real number, denominator is all real number. But when we deal with rational functions, do not bother with the numerator. Let it stay. Our concern is about those values of x, those values that if x assumes can cause denominator to become 0. And we know that according to what I have written in expanded, in a product form after I factor them, x cannot have the value of 0, x cannot have the value of 1, x cannot have the value of -1, and x cannot have the value of 7. So I wrote that one in set raster notation form, and this will be the interval notation, and that will be the sketch of graph as a pictorial to give a picture of what is happening. So now let me zoom back and say a few words, and that will be the end of our lecture. Okay then, I thank you for the opportunity. I hope that the presentation of this lecture is to your satisfaction, and I thank you again, and have a pleasant day, all of you. So long.